Okay, good morning. So this is my very first time to do a pure live streaming class. So I hope you will enjoy it. I do. Okay, so on Monday, we talked about a wave function. A wave needs to be time-dependent and space-dependent. So basically, if you have the wave equation, your solution form will be time-dependent and spatially dependent, and therefore you have a time-space relationship, and that relationship is called the velocity. Okay? So on Monday, we actually talked about the sign between time and space dependence. If you have t minus x divided by v, you have a forward propagating wave. On the other hand, if you have a plus sign, t plus x divided by v, then you have a wave propagating into the negative x direction. So you have a backward propagating wave. Okay? So the understanding to the sign versus the wave propagation direction is very important. Okay? Today, let's move forward. So we can have a very simple wave equation solution which takes on a cosine form, a sinusoidal wave. So basically you can have cosine omega t minus beta x plus some initial phase. We understood initial phase change already, but we don't really know what this beta stands for. Omega is simply 2 pi times f. Okay? So let's start to derive. So omega is nothing more than the wave frequency multiplied by 2 pi. 2 pi means 360 degrees. Okay? So we know that the solution form will be a function having time dependence and spatial dependence and somehow related through the velocity. So currently we have a solution form of cosine omega t minus beta x. For simplification, I'm dropping out the phase change. Right? So let's try to do some trick. So the solution form in the sinusoidal form conforms or agrees to my general solution form. All I have to do is take out omega. Since I'm taking out omega, I need to divide it again, right? So this thing in the bracket can be rewritten in this form. All right, so this solution form can be compared directly to my general solution form, t minus spatial dependence and divided by the velocity. So this means I can rewrite this as omega t minus x divided by v. And immediately you see that this means v for this sinusoidal wave is nothing more than omega divided by beta. So from this written formulation, we can now understand what beta stands for. Because we already know that for any wave propagating in space, the velocity is determined through the direct multiplication of frequency and the corresponding wavelength. Okay? So this is telling you omega is nothing more than 2 pi times f. So f and f cancels. So you have beta is simply 2 pi divided by lambda. So another way to appreciate beta times x is we know that for a wave to propagate for 1 exact period, which is called the wavelength, you acquire 360 degrees. So beta x is nothing more than a phase accumulation in the spatial domain. So if you allow that to propagate for a wave to propagate for exactly one wavelength, the phase you accumulate will be exactly 360 degrees, 2 pi. So 2 pi divided by lambda times lambda, you have 2 pi, right? The phase accumulation for a wave to propagate over a distance of an integer multiple of its wavelength would be an integer multiple of 2 pi. Okay? So this might be something new, but from now on you have to remember beta is just the inverse of the wavelength and multiplied by 2 pi. The physical meaning is if you allow a wave to propagate for certain length, direct multiplication to beta would tell you how much phase you accumulate. If your distance is an integer multiple of the wavelength, you acquire multiples of 2 pi's. Okay? So that's very straightforward. Do we have questions up to now? On the PowerPoint, I wrote you the definition of V in terms of omega divided by beta. And then that velocity is defined by frequency multiplied by lambda. So now you have to write it yourself. Beta is actually 2 pi divided by lambda. So with that, I'm closing the first PowerPoint set. And we're moving on to, so now we're moving on to the official content. The very first topic I'm going to deliver is transmission line. So the contents contained in this first set of the PowerPoint, there are 2 sets of PPT. In the first one, I want to talk about the general consideration. What do we mean by a transmission line? Why do we need a transmission line? And then the second step would be very important, very fundamental. I want to let you understand the difference between a transmission line and a conventional circuitry that you already learned last semester. And then, starting from something you know already, resistors, capacitors, inductors, we can construct a model for transmission line, which might be seemingly difficult now, but after you understand it, you can mathematically formulate it and solve it. You can solve everything. So eventually, after we have the so-called lumped element model, then we can derive an equation set called the transmission line equations. And then starting from there is purely mathematical derivations. But as I told you yesterday, on Monday, I don't really want you to learn electromagnetics just as mathematical derivations. I want you to understand the physics behind all the equations. Okay? So eventually, you can see that if you have a transmission line, you will have a propagating wave. And that's the reason why I started the introduction with the wave behaviors, wave parameters, and the propagation direction versus the sign. All right, so let's start. So what is a transmission line? Well, you can imagine we are enjoying the benefit of using electrical power every day, right? Right now you are using electrical power. All you have to do is plug your plug onto the wall outlet and that's it. But if you know where the power is being delivered, then you have to ask the question. Here we are users. We only have to plug into the wall outlet and we can enjoy the power, but eventually nobody wants to live very close to the power plant. right? Especially for Taiwan. If you're living close to a nuclear power plant, I mean, your housing price will be extremely cheap, I suppose, right? So nobody wants to stay near the power plant where the power is being generated. So for example, just imagine, we are living in Hsinchu, right? On our campus, where is the closest power plant? Probably a few hundred of kilometers. So how can the powers be delivered to our house or to our classroom? You have to have a lot of metallic wires, right? Metallic wires can deliver the power to your house, to your classroom, whatever, to your dorm. So basically, you would have two electrical wires to allow the propagation of electricity. Okay? So you have your generation circuit. This is maybe the dam. Okay? 的集水库, maybe you can generate power using water, and then the powers are somehow generated, stored, and then delivered over a very long distance to us. So the main question is, over a long distance, meaning this length can be very long, a few hundreds of kilometers or even thousands of kilometers. Right? So in that case, we don't really know how to solve this system. Right? So there are various geometries of transmission lines. So basically you have two metallic conductors. In the form of coaxial cable, you can have the core and you can have the grounding conductor. So both are metallic. You can have the two wires or you can have two plates. But in any case, transmission lines usually are comprised of two metallic geometries. Okay? So very clear. If we want to deliver the power in the form of electromagnetic waves, we need to have transmission lines to do that for us. So now the question is, when do we view the two metallic wires or metallic particles as transmission lines? So that's something you have to ask. Whenever you see two metallic substances, are they guaranteed to be transmission lines? Do you need the mathematical equations to solve for equal transmission lines? So that's one primary question. Okay. So I want to make it clear. As I mentioned in my PowerPoint, whether to treat two metallic conductors as transmission line or not is really frequency dependent. It's solely frequency dependent, as I will show you later. I'll just write it down. Okay. I have a transmission line. Is comprised of two metallic wires. Okay, so I have two ports. I can call it the input port and the output port. So the length of the transmission line is L, and for some reason, because I'm being smart, I already know the wave propagation velocity on this transmission line. So assume the length and the velocity are both given. So now I have to ask a simple question. If I know my V, let me use the capital letter V, okay, to stand for voltage. If I send in some kind of voltage in the form of cosine omega t, Okay? So if I know that at this location, for every time instance, I know the voltage value at the input. So now the question is, as a user, I want to receive the voltage so I can use it, right? But the question is, how do I formulate the voltage as a function of time at the user end? I don't really know, right? Okay, so the only thing I know is Professor Huang told me, oh, I know the propagation distance and I know the propagation speed. So that's all I know. But remember, Professor Huang also told me, if nothing is doing any distortion or there's no loss, this wave generated or delivered at point A should be passed on and delivered to me exactly as it is, only having some kind of phase change, right? So, if you still remember this, let me use a different color for you, okay, to highlight it. This is the general solution form for a given electromagnetic wave, right? So this already tells you if you have a wave at the input, at the output, assuming there's no loss, at the output, you still have the same wave, but after some kind of delay in time or some phase difference in space. So, I can actually erase the question mark. And I can write some equality sign. It should be omega t minus L divided by V. Let me use a bracket. Okay. A very simple mathematical formulation, but do you agree with me? Or if I didn't write it, were you able to write it down? Probably not. When I was at your age, I was not able to write down this simple equation. But try to remember, what am I trying to imply? I have a wave delivered by a transmission line. If I know the voltage as a function of time at the input, and I promised you there's nothing wrong, there's no loss, nothing going weird during the propagation, I should be receiving the same waveform at the output. Only you have to wait for a certain time, right? So that should be my output wave function in the form of voltage, right? So now all I have to do is I can just multiply things back, right? I only care about omega t minus omega L V. I only care about this term because this is the only change or difference between the input and the output, right? You have cosine omega t, you have cosine omega t, so these two are identical. The only thing different is this one. And L is a fixed length or distance. And omega is a known operational frequency. V is given for you. So this is actually a constant. Let me call it a phase. Right? We talked about the phase on Monday. The phase changes or shifts your waveform in time. Okay? So this is merely a phase which depends on your distance. So let me start to concentrate or focus on this distance-dependent phase. So this distance-dependent phase is omega times L divided by V, the traveling velocity. But we already know that omega is 2 pi times F, length, and V is, again, I'm repeating myself, but I want to make sure you understand everything I taught. V is F times lambda. Okay, so we can kill the F. So eventually you have 2 pi times L divided by lambda. This is telling you, you have a transmission line. You already know its operational frequency, or in the same way, you already know its wavelength propagating in the transmission line, and you already know its velocity. If you know its input, you immediately know its output, assuming there's nothing going wrong inside. Okay? So the wave will be delivered to the user after certain time delay, or equivalently, a phase difference. And that phase difference can be described by the ratio of the length of the transmission line to the wavelength, then multiplied by 2 pi. Okay. So now I can try to divide into two situations. When L divided by lambda is, well, smaller than 1 over 10, this means the distance of the the transmission line is very short as compared to the operational wavelength, right? In this case, that's a past. That's what you learned in the past in electric circuit. Lumped element circuit, where you have resistor, capacitor, inductors. Okay. This is something we touched on Monday. The lumped element circuit are effective when your operational wavelength is very long as compared to your device dimension. So in that situation, every position on the element can be treated to have the same voltage and the same current. So voltage and current in this assumption can be viewed as a constant across the entire element. Okay? But on the other hand, for the second situation, L divided by lambda is greater than 1 over 10. Then you have to worry, because it might be some case at a certain time you're sending in the maximum voltage, but after propagation, the phase accumulation is like pi over 2 or pi. It's negative, right? So you have a huge difference. So in this case, you need to view this delivery to wires as transmission lines. Okay? So take a good look at the blackboard and ask yourselves, are we clear up to now? The need to view the simple two wires as transmission line is completely frequency dependent. Frequency determines your operational wavelength. So if your operational wavelength is very long as compared to the transmission line, you don't care. It's just two wires. You only care about its resistance, capacitance, or inductance. But if your operational frequency is high, then you have to worry. Okay? So I want to give you some example. So C equals F lambda. So this is 3 times 10 to the 8th meter per second. If your frequency is like the tide power, 60 hertz, then your lambda is how long? Q107. So this lambda is 5 times 10 to the 6 meter per meter. So this is like 5,000 kilometers. So this is what I said on Monday. When using the tide power, because the wavelength is 5,000 kilometers, but the entire length of Taiwan from Keelung to Kending is roughly 400 kilometers. So you don't really care. All the metallic lines connected in Taiwan could probably be viewed as just lump elements, right? Under this assumption. But United States, from Los Angeles to New York, is about 5,000 kilometers. So in that case, the same 2 wires needs to be viewed as a transmission line. You will see phase dependence. You will have wave propagation behaviors. Now what happens, try to do some calculation. What happens if your F is 3 gigahertz? Why do I choose 3 gigahertz? That's probably the clock rate for your CPUs. For your computers, it's roughly 3 gigahertz. If you operate at 3 gigahertz frequency, then the corresponding wavelength is probably 10 centimeters. Wavelength. And if on the board this length is about 60 centimeters, oh, that's very long, right? So everything is frequency dependent. Even though you are using the same 2 wires, just by depending on your frequency, sometimes you need to view them as transmission lines. Sometimes you don't have to. So everything is frequency dependent. Right? So I hope I'm making myself very clear using this derivation and plus the real life examples.